This presentation is about waiting lines. You probably haven't actually thought very much about waiting lines, but if you do think about it, the experience of waiting in line is a really significant part of the consumer's experience with many, many businesses. Additionally, queues or lines are important in many manufacturing applications. We think about a company like McDonald's or a company like Disneyland or any company that operates call centers. Lines are a big deal for these guys. The experience that the customer has waiting in line, the amount of time that the customer spends waiting in line, whether or not the customer perceives that the line is managed fairly, all those things are really important determinants of the impression that the customer forms during their experience with the business. And you better believe that companies like Disneyland and McDonald's have folks on staff who understand how to manage waiting lines, how to simulate, how to model waiting lines, and so on. That they understand some of the techniques that we'll talk about in this presentation. Waiting lines don't always involve people. Sometimes in service settings, customer stuff is what's involved or what's in the waiting line. For example, at a lawnmower repair shop, I took my mower in to be repaired last April, and they told me, great, we'll repair your mower. You're in line. We'll get to you in about a month. So that was not a great waiting line experience for me. And then in many manufacturing situations, queues are a big deal. We've talked about some techniques like just-in-time that try to minimize queues, that try to minimize work-in-process inventory, but we also understand that in some very complex manufacturing situations or situations where it's difficult to predict demand in advance, particularly in non-repetitive, job shop type operations, because it is difficult to schedule. A lot of times we'll have a significant amount of work in process waiting in line at each work center, and managing those lines, figuring out how to prioritize work that's in those lines, and so on, is an important element of success. So waiting lines, which we also call queues, are a big deal, as I say here. They're everywhere and they're important in business. Let's first of all talk about some possible objectives that companies might have for waiting lines. I'd like to believe that when I go to a service business, their objective is to minimize customer wait time, but that's not always the case. Sometimes they might be more interested, for example, in minimizing the number of customers waiting in line. That's one reason why McDonald's has lots of little lines, whereas lots of other restaurants have one kind of long line. We can prove mathematically that having one long line, having everybody form one line, will reduce the average wait time for customers. But what's the problem with that? Well, it looks bad. People don't want to get into one long line. Perceptually, if we see many short lines, we're generally going to perceive that the wait is going to be shorter, even though that's not the case. McDonald's understands that, and that's why when you go to McDonald's, there's lots of little lines. Sometimes we might be interested in minimizing lateness if we're a type of business that promises due dates to customers. We might be more interested in rewarding loyalty, rewarding our best customers or our most profitable customers, rather than making sure everyone has a minimal wait or everybody has the same wait. Other times, though, we might be interested in making sure that the perceptions of is fairness to everybody. And there's lots of other objectives as well. Okay, so how do companies achieve these objectives? Well, you have to kind of break down waiting lines systematically. This may be more than you ever wanted to know about waiting lines, but we can think about a waiting line as kind of two subsystems: a customer population and a service system. So let's talk about each one of these in turn. A couple important characteristics of the customer population that are important to understand if you're going to do a good job managing, analyzing, and so on. One is the customer population finite or infinite. Finite means that there's only a certain number of people or things potentially that can get into a line or a queue. For example, if I manage a fleet of school buses and there's 100 school buses in that fleet, then I know that the line can never be more than 100 buses long for something like repair of the buses or servicing of the buses. Furthermore, if the calling population is finite, then the number of individuals that are in the line affects the probability of more individuals getting in the line. Whereas if the calling population is infinite, that's not the case. There may be 20 people in the line, but the fact that there's 20 people in the line doesn't really tell me anything about the probability of more people getting in the line. I guess technically there's really no such thing as an infinite customer population because everything on Earth is really finite. But for example, if you're Delta Airlines, millions and millions and millions of people potentially could call your call center or hit your website at any particular time to buy an airplane ticket. So for all intents and purposes, it's infinite. There's also some behaviors of the calling population that are important to understand. And here are three of them. The first is balking. Balking occurs when a person would get in line, but they see how long the line is, and they decide not to get in the line. They go home or they go somewhere else. The second one is reneging. Reneging happens when you're in a line, but because the wait is too long, or for some other reason, generally because the wait is too long, you get out of the line. So if you're on hold at a call center and you perceive that you've been on hold for too long and you hang up, you've just reneged. The last one is jockeying. Jockeying happens quite a bit at McDonald's, happens sometimes at the grocery store. That's when you're in one line, but you jump out of that line and you jump into another line, usually because the perception that the other line is shorter or the other line is moving faster. Of course, if you're like me, the line that you get in always turns out to be the slowest moving line. Okay, then the next thing that we need to talk about is the service system, and here are the elements of the service system. Let's talk about each one of these elements in turn. The first three elements are the number of servers, then the number of lines, and the arrangement of the servers. The number of servers means the number of servers doing the same job. An example of a server would be something like a bank teller, a clerk. It doesn't have to be a person. It could be an ATM. It could be a ski lift, for example. But it's the thing that's giving you the service that you're waiting in line for. Sometimes we just have one server. Sometimes we have multiple servers. We might have one teller at the bank. We might have three tellers at the bank. We might have one, baggage check station open at the airport. We might have 10 baggage check stations open at the airport. The next characteristic is the number of lines. Of course, if there's just one server, you're generally just going to have one line. But when you have multiple servers, as we talked about when we talked about McDonald's, there's two different ways to do it, right? Everybody can get in one line, and when it's their turn, they go to the first available server, or a line can form between each server. So that's two different ways to configure the service system. And then there's the arrangement of the servers, and by that we mean, is it a single-phase system or is it a multi-phase system? Remember, the number of servers is the number of individuals doing the same job, but with the arrangement of servers, we're talking about, are there multiple jobs? For example, a single-phase system would be a convenience store checkout where one clerk basically does everything. In a multi-phase system, you might have, for example, a checkout clerk and a bagger. Or at many fast food drive-ins, they're single-phase. One person takes your money, makes your change, gives you your food, and all that stuff. On the other hand, other fast food drive-thrus are multi-phase. So one person takes your money, makes your change, then you drive up to the next window, and a different server gives you your food. Got some examples putting those three different characteristics together here, what some different types of lines look like. The first line here is the most simple. Here we have a single line, a single server, and a single phase. The dots, by the way, represent items in the queue, items in the line, and the rectangles represent the server or servers. Okay, so in the next example, the red example, this is a McDonald's or a grocery store type situation where we've got multiple lines, multiple servers, and it's single phase. So there's just one server for each line, but there are multiple lines. Okay, and then the yellow, we've got a different situation where we have multiple servers, but there's a single line. Again, this is still a single phase system. These servers are parallel servers. They're both doing the same job. And then down at the bottom, we've got a situation where we've got a multi-phase system here. So you go to the first server to get part of the service, and then you go to the second server to get the second part of the service. Obviously more complicated, configurations are possible, but those configurations are just basically, combinations of kind of the basic configurations that we've got listed here. So that's the number of lines, the number of servers, the number of phases. There's a couple other important characteristics of the service system that we haven't talked about yet. One of those characteristics is the priority rules. And here are some examples of some different priority rules. Priority rules basically tell, who gets priority in the queue. First come, first served is the most basic priority rule. And that's the one that we use quite a bit, particularly in situations where customers can see what's happening to other customers. But that's not always the case. Sometimes we use earliest due date, assuming we're promising our customers due dates. It might make sense for us to work on the order that's got the due date coming up the soonest. On the other hand, it might not make sense. Another priority rule that we can use, even if we are promising due dates or if we're not promising due dates, is shortest processing time. We do the work, we do the job or the customer that we can get done in the shortest amount of time first, and then we rank them by processing time after that. On the other hand, we might do longest processing time. We might do the biggest job first, the hardest job first. Might do the highest profit customers first, the most loyal customers first. Might do emergencies first, the most urgent need first. Of course, we hope, in some settings like emergency rooms, that's what folks are doing. I'm not sure that's always what they're doing, but that might arguably be the best way to do it. It's important to understand, though, that different priority rules are going to give us different outcomes. First come, first serve is generally perceived as most fair, particularly in the West. First come, first serve is what makes sense to us. That's kind of consistent with our egalitarian values. If we're not going to do first come, first serve, there needs to be an important reason that customers understand, or we need to do something to kind of condition our customers that that's acceptable. For example, the airlines have managed to condition customers, create the expectation among customers that it's not first come, first serve, that the most profitable customers are going to be served first. But in other businesses, it's more difficult to do that. If businesses don't do first come, first serve, customers might get upset, even though the business may be serving its most profitable customers or serving using some other type of priority rule. We talked about what earliest due date is. The advantage of earliest due date is if you are in a situation where you're promising due dates or complete dates, earliest due date is going to minimize lateness. So if you've got insufficient capacity to get everything done on time, but your objective is to minimize lateness, either the number of late jobs or the total days or hours late, maybe because you're paying a penalty or just because you don't want a bunch of disgruntled customers running around, earliest due date is going to do the best job for you. On the other hand, it's not always a priority to minimize lateness, or maybe there's other more important priorities. For example, if we want to minimize the queue length, shortest processing time is going to do a better job for us. We may get more customers to get in the queue, as we talked about with our McDonald's example, if we can minimize the queue length or if we can create the impression that the queue is shorter. shortest processing time will actually minimize the queue length. In other words, it'll minimize the number of customers that are waiting in line. And that should make sense. If you do the shortest jobs first, you're gonna get those short ones, those easy ones, that low-hanging fruit in and out of the system. So there aren't going to be as many folks or as many things waiting in line. On the other hand, some jobs may kind of languish in the queue. Shortest processing time. I guess the flip side of minimizing the queue length means maximizing the number of jobs that are processed. Again, we get the easy jobs, the low-hanging fruit, in and out of the system real quickly. So if it's the end of the month, for example, and we want to bill a lot of jobs, or we have cash flow problems, something like that, shortest processing time will do a good job for us. If we're in a manufacturing situation, and a work center is early in the process, and we don't want to starve downstream work centers, or a work center feeds a bottleneck and we don't want to starve the bottleneck, again, shortest processing time, because it gets a lot of jobs through the system in a short amount of time, might make a lot of sense for us. Sometimes I do my work by longest processing time. I want to get the big job done first, the hardest job done first, because I'll feel really good, once I kind of get that job, out of my queue, get it off my mind. And I think a lot of people, particularly in white-collar settings, in office settings, tend to use the longest processing time priority rule, even though they may do it kind of intuitively without thinking much about it. Unfortunately, longest processing time is not such a great priority rule. If you're promising complete dates to people, it's not going to minimize the lateness, but it's also not going to do a very good job of minimizing your queue. It's not going to do a very good job of getting work off your desk and maybe onto the next person's desk. So even though we use it a lot, there's no real rational reason to use it. It may make us feel better, but particularly if we're working on teams and we're passing work on to other people, longest processing time is not really a good priority rule. The next important characteristic of the service system is the arrival and service patterns. It's important to understand the arrival rate, at what rate customers or other things arrive into the system needing service, and it's also important to understand how fast a server can serve a customer. It's also important to understand the distributions of the arrivals. Do all the arrivals show up at the same time, or are they evenly spaced over a time period? And it's important to understand distributions of service rates as well. We won't spend a lot of time on the distribution issue. We'll focus more just on the rate issue, and we'll just make some real simple assumptions about the distributions. It's important to understand what we mean when we say rate. When we say rate, we mean a certain number of arrivals or a certain number of service completions per one unit of time. So as it says here, for example, 6 airplanes per hour. So it's the number of things per one time unit. We can also express this stuff the opposite way, but when we do that, we're not doing it as a rate. For example, I could say that it takes 15 minutes to serve a customer, so it would be one customer every 15 minutes, but that's not expressed as a rate. To express that as a rate, we need to say 4 customers per hour. So it's the number per one unit of time. We'll talk a little bit more about that. I'll give an example of that when I do an example problem here in a couple minutes. Also want to point out here at the last bullet point that even if the service rate is larger than the arrival rate, waiting lines will still typically form. In other words, we might be able to serve 10 customers per hour and only 6 customers per hour arrive in the average hour, but because those arrivals and service times are generally not uniformly distributed, we're going to have a line build up occasionally because a couple customers might come in right on top of one another. It might take a really long time to serve one particular customer. A line is probably going to build up. Okay, so there's 2 ways to make some predictions about the performance of a service system if we know the arrival rate and the service rate. One of those is mathematical modeling, and one of those is simulation. We'll talk about mathematical modeling in some depth here in this presentation. Mathematical modeling works when the configuration is fairly simple. Those configurations that we looked at earlier in the presentation can be modeled mathematically. The most simple mathematical model is the one that we'll talk about. That's one for a single server, single queue, single phase system. When we get into more complicated configurations, where there's maybe a bunch of different queues feeding one queue and then a couple of phases, and then customers split back out into some different queues based on their service needs and so on, then we get into situations where we're kind of beyond the capabilities of mathematical modeling and we need to simulate on a computer the queues to make predictions about what will happen, what the average wait times will be, how big the lines will be, those types of things. So right now, let's talk a little bit more about mathematical modeling. We won't be getting into simulation in this presentation, but let's talk a little bit more about mathematical modeling. When we say mathematical modeling, we mean using a series of equations to make some predictions. This allows us to answer questions like what will be the average length of the line, what will be the average wait time, those types of things. In this class, we're going to cover the simplest mathematical model, and that's called the MM1 model. Here are some of the things that the MM1 model or other queuing type models can tell us about the queue. Again, the number of customers waiting in line, the probability that somebody's going to have to wait in line, the utilization rate of the server, those types of things. We're going to focus on a little smaller subset of these things in our class. Before we do that, let's talk about some of the assumptions of the model. In other words, what situations does the model fit? The model fits a situation where we've got a single line, a single server, and single phase, so the most basic type of queuing system. That was the blue diagram when we looked at different types of configurations. So this might be an automatic teller machine, for example, or a convenience store, where there's one clerk and everybody gets in line for that one clerk. There's a few other assumptions behind the model. One assumption is that the calling population is infinite. We talked about what that meant earlier. We also talked about bulking, reneging, and jockeying earlier, and we're assuming that customers don't do those things. The waiting line priority is first come, first serve. And we're also making some assumptions about the distributions of arrival times and service times. We won't really delve into those in this class. So if all these are true, if all these are the case, then there's perfect fit between the MM1 model and the situation that you're interested in. If your particular situation deviates, particularly from these things here, the predictions might not be as accurate, but the model still may be useful. Bottom line is really that it's important to understand anytime you're using any kind of mathematical model, understand the assumptions and then assess the degree to which your situation meets those assumptions. If you've got a situation that's not single line, single server, single phase, then you need to find a different model. Our book gets into one other model, and for more complicated systems, there's other models that are in more advanced books. As we mentioned before, when the configurations get really complex, then we may not be able to model them effectively. We may be better off using a simulation on a computer. Okay, so if we're doing a mathematical model, we assume that we know lambda and mu. In other words, we know the arrival rate, the rate at which customers come into the system, and we know the service rate, how many customers we can serve on average in a particular amount of time. If we know those things, we can compute the server utilization, the percentage of the time that the server is busy, or the probability that the server is busy at any particular time. We abbreviate that with either the letter P or the Greek letter rho, and that is simply lambda over mu. So that's utilization. It's also useful to think about the probability that the server is idle. So if we take 1 minus the probability that the server is busy, or P, that's going to give us the probability that the server is idle, the percentage of the time that the server is idle. If you think about it, that's also the probability of not having to wait. In other words, if I show up to a particular business and the server is idle, I'm not going to have to wait. So the probability, the percentage of idle time is equivalent to the probability of not having to wait, or the percentage of time that I'm not going to have to wait. So if we know P, we can compute some other things that are very, very important to understand. And one of those is the average number of customers in line, which we abbreviate L sub Q. To get that, we just take P squared over 1 minus P. And once we know L sub Q, we can also figure out the average time the customers spend waiting in line, and that's just L sub Q over lambda. So, pretty simple ways to answer some pretty important questions. Let's look at an example. Let's say a bank is considering adding a drive-through, and based on their experiences at other branches, they know that to satisfy their customers, the length of the line on average can't be greater than 3 customers, and the wait time on average can't be greater than 10 minutes. If they can't meet these performance objectives, they're going to have to rethink this thing. They also know, or they've estimated, that a teller can serve 1 customer every 6 minutes, and that on average 7 customers are going to arrive per hour. So the question is, given these parameters, 1 customer coming in every 6 minutes on average and serving 7 customers, or a service time of 1 customer every 6 minutes on average, and arrivals of 7 customers on average per hour, can they meet these objectives that they've got? We can answer those questions using mathematical modeling. The first thing we need to do, though, is we need to convert the service time to a rate. Remember that we said that a rate is a number, in this case a number of customers per 1 unit of time, and that's not what we had in the problem. A lot of times when we're measuring service times, we figure out what's the service time, and in this case we know it takes 6 minutes to serve a customer. So to convert that to a rate, we've got to say, well, how many customers is that per hour? Since our arrivals are in hours, let's express our service in hours as well. So we just take simply the inverse of the service time to get the service rate. In other words, take the inverse of 6, or 1 over 6. To convert that to number per hour, we need to then multiply it by 60. Let's break that down a little bit so it makes sense. If we say 1 customer every 6 minutes, that's the same thing as saying 1/6 of a customer every minute. And 1/6 is simply 0.16, so that's 0.16 customers per minute. Again, we need to convert that to hours. To do that, we just multiply by 60. So 0.16 per minute is the same thing as 0.16 times 60 customers per hour, or 10 customers per hour. So that's our service rate. Now we've expressed it in a number, 10 per 1 unit of time per 1 hour. So that is the Greek letter mu, or the service rate. So now we've got our service rate, and the problem gave us our arrival rate, so now we can do the calculations that we looked at a couple of slides ago. Remember, P, or the service utilization, is just equal to lambda over mu. So in this case, that is 7 over 10, or 0.70. We weren't asked to compute the probability that the server is idle, or the probability of not having to wait, but that's always a good thing to do, and that's just 1 minus P, or 0.30. So now let's figure out what's the average number of customers in line going to be. Remember, to do that, we take P squared and divide that by 1 minus P. I've done that right here, and that's about 1.6 customers in this line on average. If we know that, we can also compute the average customer wait time, or W sub Q. And to do that, we just take L sub Q and divide that by lambda, and I've done that here, and if you do the math on that, you'll see you get 0.23. Now, recall that our lambda and our mu were expressed in hours, so that means that this is going to be expressed in hours as well. So in other words, the 0.23 refers to 0.23 hours. So to convert that to minutes, we just multiply it times 60. If you multiply 0.23 times 60, you'll see you get 14. In other words, 14 minutes is your average time spent waiting. So, unfortunately, we're not going to meet our wait time objective. Remember, our wait time objective was 10 minutes. So there's some different things that we can do. We can make some investments in teller training or automating the teller process or doing something like that to decrease the service time or increase the service rate. We might also think about adding a second teller, so we have two parallel servers, or maybe we can break it up into a two-phase type system. That might work better if it's a fast food restaurant than a bank, but there may be some way to do that. Bottom line, our mathematical modeling suggests that as is, the system's not going to meet our needs, so we need to try some different things.